That's meant to be like the first big research part of the program. I hope that all of you have managed to register with the secretaries. If you haven't, then please do. They'll give you all the practical information and so on. We are going to have a reception today at 6 o'clock following the lectures, so there should be a nice kind of way for everyone to start off the week. And on Wednesday, there will be a conference dinner, and I think you should have received an email about that, so please reply to it if you want to come or have dietary requirements. Finally, of course, we're going to be providing lunches and coffee breaks here, so you don't have to do anything other than show up. And the final bit of practical announcements is that if you write any papers while you are here, we would please like to ask you to acknowledge that you were visiting GGI during that and during the time. Okay, so we'll kick off with Alejandra Castro, who's going to tell us about Siegel modular forms and black hole entropy.
Okay, so feels a bit awkward, but I would like to thank the organizers for giving me the opportunity to give a talk. And yeah, indeed, the theme of today, well, not today, of this entire week is black holes. And so we're going to start this week with the right footing, and at the center of this talk, actually, there's going to be a black hole. This talk is going to be all about black hole physics. Not this black hole in particular, and not understanding all this complicated structure that is around this black hole. But the question that I would like to ask, and it's a question that has been hunting string theorists for a very, very, very long time, is basically, given that we know that black holes can carry entropy, in particular Wittgenstein-Hawking entropy, is it possible to write down the entropy of a black hole as the logarithm of the degeneracy of microstates? Okay, does that equality make sense? When does it make sense? How does it make sense? What are the microstates behind that? So string theory, I'm preaching to the choir here, it provides us with examples where this equality holds and when we have a lot of control on both sides of the equations. And in particular, on the gravitational side of this equation, there's the leading piece, the most famous one, the area law that comes with a very specific coefficient, 1/4 g Newton. But as well, within the framework of string theory, there's a plethora of corrections. They come in different shapes and forms, but roughly speaking, in a nutshell, there will be quantum corrections, there will be higher derivative corrections, and so forth. Okay. Yeah, one of them will be local, and the other ones will be like non-local. So one loop corrections of massless fields. That's what I'm calling quantum corrections. Yeah, but they come like, I'm thinking this more of like alpha prime corrections, if you wish. But I'll talk a bit more about this quantum corrections in a moment. So the focus of this talk is trying to make sense of this equality. And in particular, what I want to do is to show how to build statistical systems. So basically, I'm going to focus on this d micro. So I want to show how one can build statistical systems that have the capacity of describing the entropy of a black hole. Okay? And I will explain what that means. What does it mean for d micro to be compatible with a black hole interpretation? Okay? Now, this was work done recently with 3 wonderful collaborators, 2 of them postdocs in Amsterdam, and well, Joao is also a postdoc in Utrecht, and Christoph Keller at ETH in Zurich. Okay? So very good. So what is the general strategy that I'll find, that we used throughout our work? Basically, you can break it down into 4 different pieces. So we basically tried to find inspiration from known examples in string theory. So we revisited results that are well known in the literature, that have been studied for quite a bit. And we said, okay, what was the key? Can we draw some lessons and find some inspirations on those very exact and precise computations? Then the other thing that will be another theme of the talk is basically exploiting some symmetries of the black holes. We also want to exploit holography, try to make use of what we learn about holographic systems and the holographic correspondence. And in particular, the most novel part is to exploit number theory. So I want to build counting formulas, I want to build these statistical systems, and number theory will be incredibly powerful and useful in order to do that. Okay? So the way this talk is going to be divided is basically going to be divided in two. So I'm going to spend a bit of time on the microscopic side because I want to know what is my input. I want to define for you what do I mean by a microscopic system having black hole features. So we're going to revisit what are the basic properties of these black holes. And then using that universality, I'm going to go and search for my partition functions, okay? So I'll try to nail down what are certain classes of systems that have the right features to describe a black hole. And so as we go along in this journey, and as you will keep on asking me questions, you will notice that I'm going to start putting myself in a little box and going into a little corner. And so my first corner is that I'm going to be discussing today extremal black holes. Okay, as a first approximation, okay, the first thing that I'm going to do is discuss extremal black holes. So this picture that I originally showed to you, this is too complicated. This will be something like the Kerr solution. It's too hard for me right now to digest this. Worthwhile thinking about, but not the focus for today. So I will like something like this, okay? So this is going to be my version of what I'm doing, and I have like a little, like my spherical cow, okay? So I want to remove all the distractions that comes because you have interactions and gravity is complicated. And I just want to focus basically on the horizon itself, okay? And what can I learn about properties that are intrinsic to just the horizon? And extremality does that trick for me. So as it's known, let me just recap what are certain properties of these extremal black holes. So first of all, usually black holes that are either rotating or charged have an inner and an outer horizon. Extremality means that these two horizons coincide. So it's a degenerate limit. The surface gravity vanishes for the systems, which implies that there's zero Hawking temperature. And what's key as you go through this is that there's an enhancement of symmetry. So if the horizon originally had Rindler symmetry, as you take this extremal limit, the near horizon geometry will have an ADS enhancement, an ADS2 in particular. The solutions can be supersymmetric, which as a theorist you always get excited. Even more symmetry always gives us more control. So it's something that you can exploit as well. But the very interesting feature of this limit is that there's the area of the horizon is finite. And so it means that as you go to zero temperature, there's a huge amount of entropy. And this has always been like the big puzzle. So this is where there's always conservation of difficulty in this problem. I gain quite a lot of symmetries by going to the extremal limit. But the big problem that extremal black holes present to us is that there are systems, there will be statistical systems with a huge amount of ground state degeneracy. Okay, so this, if you want, is a bug, and the other ones would be features. And so pictorially, my cow, the way the cow looks is that I will be thinking of systems that are asymptotically flat. This is mostly because these are examples where I have control in string theory, so there will be solutions that are asymptotically flat, but as I take the near horizon limit, the near horizon has, in the most simple cases, it has a factor of like ADS2 times S2. So you develop this infinite thread. Yeah. Like most of my equations will focus on things like this because this is where I understand it better. But I think that a lot of what I'm saying should be thought and tried to be extended for more generic types of extremal black holes. But because I'm drawing so much intuition from string theory configurations, this is a safe place where to start or where to understand how various details come in about and how to kind of extend above it. But of course, what it will be interesting is understand when you have rotation, and then here you have vibrations, and that will be, it's an extra layer of complexity. But just for simplicity, let me just sort of start with the most simple configuration, and this is one of them. So to put equations into this, okay, so how do these solutions actually look like? So this near horizon solution looks as follows. So here I'm considering something like the 4D rhizonostrum in the extremal case. I'm not having rotation, just for simplicity. The solution will carry both electric and magnetic charges, and there's an extremal limit for which the near horizon geometry has that form. And so there's two scales here, the ADS scale, the ADS radius, and the sphere radius. And both of these parameters, notice they're the same. That's the equations of motions. The Einstein-Maxwell equations forces both of those parameters to be equal to each other. And the solution is supported by some set of electric and magnetic charges. Electric charges are basically proportional to the volume of ADS2. The magnetic charges will be proportional to the volume of the S2. And the equations of motions as well relate these parameters L to these electric and magnetic charges. And so in the example that I will have in mind, this is basically the relationship. So now you'll start getting annoyed with me because I'm going to write a lot of squiggles, and it's because I'm not keeping track of numerical factors. They're not going to be important, but if you go through, there's factors of 2 and okay. So give me a break, but what will be important here is how things are scaling, how things are related to each other. So what I want you to keep in mind is that the radius of the sphere squared goes like the square root of q squared times p squared. Okay, so this is the important scaling. And of course, the area of the horizon is just the volume of this S2, so the entropy goes like this radius squared. Okay, so this is the geometry. These are some basic properties of the geometries. But now, as we try to define what S black hole is, I need a framework. I need to know what am I computing, and in particular, I'm interested in corrections. So here I'll follow Ashok-Sen work. So the way he quantifies entropy for these solutions, he defines what's known as the quantum entropy function. So this object is something that has a set of boundary conditions. So that's what this subscript here is trying to relate. It's like, what are the boundary conditions that focus on a black hole and a single center black hole? There's a path integral over all fields, including the metric as well. And there's as well an action, a gravitational action, that includes all sorts of local corrections as well quantum corrections. And from this point of view, Ashok also told us how to understand this holographically. So he was interpreting this quantum entropy function as basically the degeneracy of a one-dimensional quantum mechanical system. And the black hole entropy is basically a suitable derivative of this quantum entropy function. So this factor here, L, is basically a large volume type effect. Okay? So in gravity, what you will think of, if you have the power of not just doing two-derivative gravity, but doing making sense of what this path integral is, the definition of black hole entropy will be given by this formula. Okay, so this is Ashok's proposal of how to think about a black hole entropy for the extremal situations. Yeah, it's because it's a length scale that is inside of the ADS2. You're at 0 temperature, so there's no length. So that's why, like, the length is going to infinity. So temperature going to 0 is like beta going to infinity, and that's what this is reflecting. So that's why it's a ground state degeneracy. So the thing that survives in this formula is just a ground state contribution, and then you read off what d micro should be. And then this formula is basically projecting out this contribution without ambiguity about how you regulate various divergences. Whatever Ashok meant by CFT1. So he's basically saying there will be some dual system to this ADS2. We're not going to put in too many details. Nowadays you can say words like SYK or in my case it will look more like the BPS sector of a 2D CFT, but basically whatever system, if this has a good trace interpretation, it should have this type of behavior. That's the point. Well, he's just declaring this as a definition. I'm going to identify this object as this. And he's saying, because of the various divergences of properties this object has, it should asymptote to this expression, and this is the quantity that you're evaluating. But okay, so let's say I want to just do the leading, I want to understand the leading contribution to this object. And in the leading piece, what I mean by that is when the theory is both basically governed by just Einstein's theory, okay? So I have a very large black hole, very low curvatures, and so the geometry is very weakly coupled. I'm going to center on a, well, I'm going to look at the case where the single center black hole is the most dominant solution. And in this case, the microscopic formula has, as I've said already, the area contribution, but then there's as well a subleading contribution to this formula, which is coming from the massless particles that you have in this two-derivative theory of gravity. So if you do a one-loop computation of your two-derivative effective theory, there's going to be loops, and those loops will give rise to logs, and there's going to be a coefficient multiplying this log, and it will depend on basically which two-derivative theory you had in particular. Okay, so if you had how many vector fields, how many hyperfields, if you had gravitinos or not, all sorts of quantities. So what I want to emphasize here is that a two-derivative theory of gravity doesn't make just one prediction, it makes two predictions. Okay, it will tell you that the leading contribution is the area, and then there's a next to leading contribution that is just governed by the same theory that comes with a logarithm and a particular coefficient multiplying that logarithm. So the challenge here right now is to find statistical systems with a huge amount of residual entropy. And the opportunity that we have is that we will be able, as we try to build these statistical systems, there's two quantities that you have to at least make sure agree with whatever model of quantum gravity, whatever model of microstates you might have. So along those lines, I always like to quote one of Ashok's papers on this. So I strongly recommend you, if you're interested in this subject, to read this paper. And in particular, the abstract is already quite powerful. And so the font in the abstract is a little bit small. So let me just highlight two sentences in that abstract. So basically, Ashok makes a case that the logarithmic corrections are computed just in terms of low energy data. And by trying to reproduce this on the microscopic side, it actually gives very, very strong constraints. So let's now move on then to the microscopic side. So what is this man talking about? So on the microscopic side, you will have some counting formula, and I have to be able to reproduce these quantities. So what has been done? So okay, so this is a very, very quick snapshot. It's not a complete list of everything that has been done, but just to give you a flavor of the types of successes that has been reported. And most of this work in reproducing the macroscopic and microscopic side comes from work of Ashok with various collaborators. So here I'm highlighting, so there's this formula, the area plus the log. And as you can see here, depending on the theory, so these are different examples of theories. Most of them are 4-dimensionals. There's also 5-dimensional examples, the BMPV black hole as well. But what you can see here, what's interesting about this table is how this coefficient changes depending on which theory you are at. So for instance, if you're n equal 4 supergravity, the coefficient is actually 0. You're n equal 8 supergravity, it's -4. N equal 2 supergravity, then it depends on the number of hypers and the number of vectors that your theory has. As well, in the BMPV case, there's a dependence on the number of vectors that the 5-dimensional supergravity contains. Now, what do we know on the string theory side? So here is where check marks and question marks comes into hand. So when we do know what the microscopic counting formula is, when there's a proposal of what is the D-brane system and what is the appropriate object, Ashok very carefully showed that both the gravitational computation and the microscopic computation agree. N equal 2 is a little bit controversial. There is something that one can say, but the counting of n equal 2 black holes is much more difficult, so then that's why it still has a question mark there, but maybe one can write a check mark with a little cross, because some things are known, and if one makes some assumptions, you can reproduce this, but it's still a bit murky. Okay, and I should also point out that apart from the results here, there has been as well in the past years by the group of Finn Larsen and collaborators at Michigan, they've also been exploring and evaluating more of these log corrections for even more types of black holes that are not necessarily supersymmetric in 4 dimensions. So there's a long by now literature on reporting and keeping track of what are these logarithmic corrections. Yeah, so there's a combination. So actually Finn noticed that a couple of years. Ashok did it for the non-extremal case for Schwarzschild, and it's his famous challenge to loop quantum gravity. that loop quantum gravity, if they claim that they can describe the entropy of the black hole, then they should also get correct this number, and they can't make up their minds on what the number is. So I know, but then they kind of say, oh, but if you tweak this and you tweak that, then you can get this other thing. And then Ashok, I think, lost his patience. and it's kind of like, yeah, okay, let me know when you guys come up to... Yeah, but like the historically known report of what value loop quantum gravity gives does not give this right answer. So that was disappointing. But then, for instance, Finn explored as well very carefully the non-extremal solutions. And there's very beautiful results in that case that are quite surprising, that the log corrections are so robust and so, like, they look like protected quantities, and it's not clear why, and it's not clear what's taking. But the thing that Finn did that was not something that Ashok did is that Finn actually looked at the corrections for the non-extremal cases inside of supergravity. Ashok just did it for a generic Einstein-Maxwell theory where everything was minimally coupled. And then the work that the group in Michigan has been doing is actually saying, okay, let's look at how these corrections look in supergravity with a string theory interpretation. And actually, there's a huge simplification when you do that. And there's very beautiful answers that have not been yet interpreted microscopically. So there's a lot of data, and that's why I'm advocating. These corrections are telling us something about the microscopic description, and I think they deserve to be explored. What's that? No, there's not. But that's why it might give a hint about what's happening, what are the structures, what is special about string theory, why can you not UV complete a random theory? So there's something there. I'm not sure what is it yet, but I think it's worth thinking about and kind of appreciating that there's a really beautiful structure in this types of solutions. So, okay. So with that impressive table, so what I'll do, my first input is to say, okay, let me look for statistical systems that are described by a 2D CFT, and I'm going to look for these highly degenerate type of statistical systems. So what is my justification? Well, the success list that I showed you before, even though there were 4D black holes and they had near horizons of ADS2 times S2, this ADS2 geometry has, in many cases, an ADS3 origin. So this is, again, my second time that I put myself in a corner. So I'm not just studying a generic extremal black hole, but I'm going to be studying a black hole that I could lift to something that looks like ADS3, okay? So you can't always do this, but in many, many cases you can. So, okay. So what does holography tell me about this? So if I go and look at my dictionary, okay, so on the gravity side, let me say I have this VPS black hole that had electric and magnetic charges. In a CFT, the variables that I will be using are the central charge. I'll have some energy, well, some chiral energy, and some Kac-Moody current as well. Now, the dictionary between these variables for the example that I presented to you goes as follows. The central charge roughly goes like Q squared, the energy like P squared, and the current is like q dot p. Okay? And the claim of holography is that the black hole entropy should be equal to the log of that microstate counting. Great. So I have a CFT2. So in the CFT2, I can define its partition function. If I'm doing supersymmetric computations, I should put a -1 to the f. It's actually an index. But okay. So I have this partition function that will depend. I'm summing over the values of L0 and J0s, my energies, and the current values, and here are the chemical potentials that I'm going to call Q and set. And, sorry, that's a Y. So Y is e to the 2 pi I set. Sorry for that typo. And basically you can say, okay, can I estimate the asymptotic growth of states? Yes, you can. That goes under the name of this Cardy regime. So the degeneracy of states is just basically this integral of the partition function weighted appropriately, and universally you find this expression. And so then you use your holographic dictionary and you say, A over 4g Newton is 2 pi, is exactly this. So you use a dictionary that I used in the previous slide with all the numbers and coefficients correctly. Bam. Okay, great, fantastic. ADS3 CFT2 reproduces the black hole entropy. We're all super happy. Done. So, are we done? No, we're not done. There's a big but. Okay, so the problem in this derivation, it's very impressive, and there should be nothing like. It's extremely suggestive, and it's great, and it's in my point of view, a minimal requirement of what should be happening. If this doesn't happen, then everything is lost. But it's not sufficient. Is it not sufficient? Well, when you get this formula, you use modular transformations, various symmetries of the partition function. But the most important point that I want to highlight is that there's a saddle point approximation. And the saddle point approximation is only valid when the energies are much bigger than the value of the central charge. Okay? This is what goes into the plain vanilla, the most boring derivation of the Cardy formula. And now, if you remember and you keep track of what happened with my dictionary, and when is the black hole big and kind of weakly curved. The black hole is weakly curved when the area is much bigger than the Planck length. And if you look here at how the dictionary looks like and what this implies, this will tell you basically that the black hole is weakly coupled and dominant when the energy is of order of the central charge and both of them big, which is not the same as that regime. Okay? So what you actually need is to be able to get that amount of entropy and that exponential behavior here, okay? And this is not generic. Not any CFT2 will have a Cardy regime when the parameters scale in this way, okay? So this is not typical. And moreover, if you look at, let me go back just for a second, since I've been yapping about log corrections, you can also compute a log correction here and compare it to my table, and guess what? It's not going to match. So the Cardy regime does not reproduce the logarithmic corrections that I very carefully listed with all its parameters and its glory. So that's another way you can convince yourself that that's not the right regime to study these ADS2 black holes. Okay, so that universality was not enough. We need to start digging in more and more. And so what is the second input? The second input is that I'm now going to average over theories, okay? And as I average over theories, I'm going to advocate for a new symmetry. And the symmetry will give rise to this new object that is known as a Siegel modular form. Now, what is my justification to do this? It's because that gives me what I want, okay? So, as blunt as that. And it was the key for the known examples. So let me understand what that symmetry is and how can I exploit it and how can it gives me what I want. I'm not going to advocate that this is the only way you can get this huge amount of entropy in the right regime, but I do want to say that it's pretty powerful. So it should not be should not be neglected or think that it's very unique to the known examples. Okay, so here's how it goes. So I told you I was going to average over theory. So imagine each partition function that I had before depends on basically, very crudely speaking, what central charge I have and what I'm doing. roughly speaking, is summing over central charges, where I introduce a chemical potential for that central charge. Okay? And then what we'll do is look at this type of functions and try to identify when can I get this exponential growth in the right regime, and basically extract the further subleading corrections to that formula. Okay? So a Siegel modular form is basically one of these forms, but it has an extra input, an extra symmetry that is not generic. And so the symmetry is as follows. So the easiest example, and this is the one that was studied a lot in string theory, is that this as a generating functional, this curly set, has an exchange symmetry between tau and rho. Okay, so between P and Q, if you wish. So if you exchange the roles of P and Q, the object is invariant. And this defines, combined with the modular transformations of the original object, it defines for you the group SP4 set. So it enhances the set of modular transformations. We'll also be considering cases where it's not just tau to rho, but you can also take tau to n times rho, or rho, and rho goes to tau over n, and then this defines a paramodular group that is very, basically, think of it if you want, just as this one as well, okay? So when I refer to Siegel modular forms, I'll just be sloppy and I'll be referring to this both cases at the same time. And so the way these objects transform is basically like this. So it's convenient to define a 2x2 matrix where the potentials are encoded, and this is the modular property of a Siegel modular form. And these entries, A, B, and C, they're 2x2 matrices that define that satisfy these constraints, okay? So that's SP4 set. Okay, so for this classes of forms, I'll now consider doing my asymptotic behavior, okay? So I'm going to try to understand what is the degeneracy of states for the Siegel modular forms. So in the known examples, it's U-duality. It's electromagnetic duality. So exchanging rho and tau. So remember, C went like. So exchanging rho and tau basically exchanges the role of C and E, and so it exchanges electric with magnetic. So in the n equal 4 case, this is basically the key symmetry. So I'm basically trying to say. Exactly, yes. And the way you go about, and this is a procedure that Ashok used and we generalized, was to basically, okay, you consider this object, and this object now, 1 over the Siegel modular form, is a meromorphic object that contains zeros and poles, and so you can do a residue integral over this object. The main task is to find what is the most dominant pole given some scaling regime of the charges. And then to estimate the leading part, you can do a saddle point approximation. So for instance, the example that many of you might be familiar with is example where the Siegel modular form is a Igusa-Cos form, which is known as phi 10. And on this object, because I should be speeding up a little bit, this object basically is built out of the elliptic genus of CFT with target space on K3. Okay, there's various, it's not just the partition function or the generating function of the CFT. This exponential lift also counts center of mass degrees of freedom and KK monopoles along the right. But basically, the main input of phi 10, what defines phi 10, is this object here that is called phi 01. And I wrote it here in terms of theta functions in case you remembered it from some string theory course. But okay, but this is the object that counts a quarter BPS states in 4D supergravity. And this object, this function, which is the Siegel modular form, is the one why you see these 3 check marks, okay? So that's the object that was used on these 3 lines. Very good. But what's cool about this is that now if I take this perspective and I dig a little bit in the math literature, This is not the only function that has this form. So Gritsenkov and Nikolin in 96 and then in 99 had a series of papers where they showed a theorem. And the theorem, we find it quite powerful because it basically tells you, grab any Jacobi form that you want. We'll define for you this exponential lift, which tells you basically how to build out of something that just depends on tau and set. It also has the p dependence encoded in here, and there's dependence on the Fourier coefficients of this Jacobi form. And they basically show that this is an object that transforms under the paramodular group. Okay? Moreover, this formula is pretty powerful because the input is really minimal. You just give me what the Jacobi form is, and then I'll generate for you this more bigger object. And as well, these mathematicians were so kind to me that they told me where all the zeros and poles of this function were located, so I can easily do residue integrals for this beast. We know how to, basically, the main portion of our paper was to how to systematically extract the Fourier coefficients of these objects. And we, along the line, we could identify new examples that had these black hole features and were not phi 10. And so just to show you that there are non-trivial examples, these are three non-trivial examples of these Siegel modular forms that have black hole features. And here I basically showed what happens to the log corrections as you look at different regimes within these functions. So what I want to illustrate here is that depending on which regime you are, these logarithmic corrections can change, and usually the regime that most of the time the regime that Ashok was looking at was this one, this middle one. And this first one over here is like the Carty regime. And what I want to highlight is just how different these corrections look like, and that's why it's non-trivial to get the right answer when you need them, okay? So here, the correction just depends on the weight of the form. It's kind of the boring correction. Here, the correction actually is sensitive. This M11 is data of that Jacobi form, and it's quite sensitive to the microscopics of the theory, okay? So it's microscopic data that is controlling those corrections. But okay. So, and we have more examples than those three listed, but time, I have 2 minutes left, so I won't be able to go through all of the examples, but I just want to kind of summarize that as all this dust settles and you go and explore these different types of modular forms, you'll basically have, we can tell you when you're going to have modular forms with the right features, basically that you have a large amount of degeneracy in a regime of interest, and you'll be able to make a prediction on what this correction is and compare it to your gravitational theory, okay? Among other corrections, among other subleading corrections, okay? Very good. So, where do we go from here? We drink some water. So what I want to highlight is that these modular functions, they might not be the most universal thing that you can do with ADS2, but they're still pretty powerful within this arena. By postulating this new symmetry, we're capable of building many partition functions that have black hole features. And that's a highly non-trivial text. That's usually what people complain about, that black holes carry too much entropy. We can basically, since we can extract the Fourier coefficients quite easily, we have a very precise sort of prediction of how this object behaves, and so you can make a very sharp connection with the gravitational results. Now, what are the bad news? Well, what are the challenges in a better line of thought? So what I have not told you, if you notice, is that I didn't tell you, basically, I kind of hand-wavedly told you how the black hole charges are related to this data and the Siegel modular form, but this is actually important because it governs the scaling, okay? The dictionary between the black hole parameters and the parameters that go into the Siegel modular form tell you how this object scales, and I just want to illustrate to you that the two examples Sometimes you get that C is of order E, like in this example here, but in 5 dimensions, this guy, for instance, actually goes like Q1, Q5, and this guy just goes like P. And so actually the regime that is more natural is C much bigger than E. Okay, so depending on how you map various parameters on the Siegel modular form, you might find different scaling regimes that you need. And so that input is important, and we have not digested it fully because we basically don't know what the black hole is that we're studying. So I have these new examples of partition functions, but I did not tell you what is the gravitational theory that I was studying. And I also didn't tell you what is the CFT that I'm studying. So these are two basically important questions that now I have for you, the partition function. What is a theory? Okay, I don't think this is an impossible question to answer, but it's something that we're thinking about, and we're trying to understand what are the CFTs, what will be this gravity dual, what will be the string compactification that we would attach. And yeah, so view it as an open question or an attack point, as you wish. But more generally, again, I want to rephrase that we postulated this non-trivial symmetry. You might wonder, is this a necessary condition? Is this a sufficient condition? Or perhaps it's just an approximate symmetry that maybe in the limit that you're interested, you have this electric magnetic duality, but it might be broken, and how can you quantify that from the CFT point of view? And again, just to make an advertisement, it's important, as I was asked before, like these log corrections are really, really powerful, and they can tell you if you really are in the right regime, if you have the right object. It's a first step in trying to do precision counting of black holes. So thank you very much. Yeah, so this exchange symmetry is not enough. So I do not any Siegel. So I should not be misleading. Not any Siegel modular form will have this wonderful property. So we do discuss which ones will, and it's connected to that sparseness condition because we have, for instance, Siegel modular forms that have Hagendorn spectrum, so that you can also like quantify and see, this thing is Hagendorn, it's not Cardi. And so in our language, the sparseness condition, we don't have to enforce it by hand. We don't have to say, oh, we want a theory with a sparse spectrum. It just comes about of the analytic properties of the Siegel modular form. So if we look at Siegel modular forms that just have certain classes of poles, then we get by free a spectrum that is sparse, and that's something that we're trying to figure out right now. What is that sparse spectrum? So what is the density of states at very low energies? Not in the black hole regime, you're always at high energies. So now I'll be interested in the low energy regime and understand, okay, what is a gravitational spectrum? And that's why I think that I can know what the gravity theory is, because I'll be able to read off like what is the number of gravitational fields and how they organize themselves in terms of multiplets and so forth. But yeah, so the successful examples have a sparse spectrum, and we're in the process of digesting the details of that sparseness.
Also did an averaging of the theories. Yeah, you also had an averaging of the theories, so
yeah.
What does it mean?
That is an interesting. I've got that question before, because in some sense we've used it. It's not like this example of the DVB formula is not new, right? It's like these guys used it in like 95 or so. So I'm not like making a big revolution, but from a holography point of view, it sounds strange because I'm telling you average over central charges, and it feels like you're averaging over gravitational theories. But in some sense, I think it is something that we should not be afraid to doing in holography, because we want to extract the large C limit, right? And the large C limit by itself, as it stands like face value, is a very difficult limit to access. And what you do by averaging is that you're basically trying to understand the typicality of that large C limit. And that's what the averaging over theories allows you to do. It allows you to extract from the statistics, what is the thermodynamics of a large n type limit. And so right now, my point of view is that I view it as a very handy trick in order to extract large C behavior. If it has some more deep meaning about how we should view holography and how we should interpret the holographic dictionary, I'm not sure, but it's, I don't know, and I can get quite a lot out of it, so.
So you already had some comments on the electromagnetic or U-duality. First, is it possible to understand this averaging over theories that you mentioned by as just U-duality completion of partition function for one of these theories only?
That is one way how you can think about it, yeah.
Okay, so there is one handle on this, so it's not just it reproduces what we wanted to get.
Sorry, I couldn't.
So if we want to write down the partition function, which is U-duality invariant, so that's one way to justify this.
Yes, yeah, it makes the symmetry manifest, so it makes it very clean how to.
Again, on this electric magnetic duality or U-duality, it could be used to relate large C versus large E limits, right?
Yes.
So it's not strange that you capture both cases.
Yeah, no, in some sense, the symmetry kind of gave me that for free. So,
okay,
yeah.
so it was, in a sense, an input, if you wish.
Yeah, no. The symmetry is an input. I'm not justifying the symmetry. I'm putting it as an input, and I'm the thing that we were afraid of is that this function phi 10, the famous one, was going to be the only one that had the right properties. And what we discovered was that no, there's actually different classes of functions that are in the same universality class. But no, indeed, it is an input. I'm not justifying it. I'm just saying, okay, let me consider this extra symmetry and see if there's non-trivial examples within that. Because there was a lore in the community that phi 10 was very unique, and at least in the microscopic counting people, like it felt like it was very kind of specific, and you couldn't kind of wiggle with it or move around too much with it. That was at least my impression. And so yeah.
And again, on this U-duality, you have examples which are, the near horizon is like ADS2 cross S3, and in some dual picture it's ADS3 cross S2. Can we learn anything from this ADS3 picture? Anything?
From the ADS3 picture?
Yeah, just if you go to some dual description, you have a different black.
So the ADS3 picture is very useful because it tell me how the map will go. It will tell me something about, okay, how do I map the gravitational parameters to the CFT parameters? So I think that's basically why I need the ADS3. But basically, I'm viewing it as a lift. So I have an ADS2, I will lift it up to an ADS3, and then I will say, okay, the putative CFT will have this values of central charges, and the way they're related to the ADS2 parameters are in this way.
I meant more to determining what the 2D CFT, dual 2D CFT is. So it's like checking things about sparseness of the spectrum and things.
Oh,
like
yeah, of course. Yeah. The sparseness part comes from the ADS3 point of view. Yes. Yeah. The counting of polar state, that lower part comes from there.
In the case of non-magnetic charges, from the microscopic counting, the entropy also seems to vanish. Is that right? Could you elaborate on that?
That's a bit, yeah, I know. The way I wrote down the formulas, it looks like, if I put Q or P equal to 0, there's a problem. No, there's not a problem. Like, you can make the solution purely electric or purely magnetic. The dictionary will be modified slightly. I'm just writing it to make manifest the U-duality symmetry. But there's not a problem. Actually, the n equal 2 black holes, for those of you that are familiar, like like the frame that people like to write this is where C goes like P cubed, and the energy just goes like one of the charges, like this Q0. So this is like the intersection number of the Calabi-Yau. But you can write down them. And n equal 4 is just nicer to write it like this, but there's different, like you just have to do a duality frame transformation, and then you can make the solution purely electric. But then the only important thing is that you have enough charges so that the solution has a big horizon. That's all. If it's purely electric, just to, let's say that you just have one Maxwell field, what will happen is that this thing will kind of look a little bit degenerate. So I would have written down something like this. That's all. So I know it looks a bit weird, but it's not. If you go through the formulas, there's not a problem.
All right. All right.